So in this video we're going to prove theorem 3.31 that says if U is the supremum of the set E, where E is some subset of R, then that's equivalent to saying that for any epsilon greater than 0, no element of E is greater than U plus epsilon, and there is an element of E greater than U minus epsilon. So what I've done up the top here is I've written that statement in mathematical language. So U equals sup E for some E subset of R if and only if for all epsilon greater than 0 and for all x in E, x is less than or equal to U plus E, and there exists an x naught in E where U minus epsilon is less than x. So if you think about what that's saying, it's saying that being the supremum of some set means that you're somewhere between U minus epsilon and U plus epsilon for epsilon as small as you like, and if you make epsilon really, really, really small, then what's going to happen is your supremum is going to be this U here that we're talking about. So we're going to prove that. First we're going to start proving it in the forward direction, and then we'll prove the converse. So let's start with the forward proof. So we're going to start off assuming that U is equal to the supremum of our set E, and we're going to look at any element x of E. It's true that in this case U is greater than or equal to x because we've already assumed that U is the supremum of E. So the fact that U is greater than or equal to x comes directly from the definition of what it means to be an upper bound. So once we've established that inequality, U is greater than or equal to x, then it's also true that for each of these x's in E, U plus epsilon must be actually bigger than x. Why is that true? Well, epsilon is a positive number, U is already greater than or equal to x, so that means when I add something onto it, it must be actually greater than x. So that means if U plus epsilon is greater than x, it is also true that x is less than or equal to U plus epsilon. Remember, we have this idea of even though we've got strictly less than, we can always say less than or equals because we're using the word or. So that just tells us immediately that condition 1 is satisfied. So to show that condition 2 is true, we're going to use proof by contradiction. So condition 2 says there exists an x naught in E such that U minus epsilon is less than x. We're going to assume the opposite. We're going to suppose that that statement is not true. So there exists an x naught in E such that U minus epsilon is less than x. What does that mean if we negate that? It means that for all x in E, U minus epsilon is greater than or equal to x. If that's true, for all x in E, U minus epsilon is greater than or equal to x, that means that in this case, U minus epsilon is actually an upper bound of E. So remember, the definition of an upper bound is some number that's greater than or equal to every single element in X. So that comes straight from the definition of upper bound. And it's also true that U minus epsilon is less than U, since of course epsilon is greater than 0. But that's a contradiction because we've said U minus epsilon is an upper bound that's less than U, but U is in fact sup E, which is the least upper bound, so there are no upper bounds less than it. So our assumption must be false, and the original statement is therefore true. There exists an x naught in E with U minus epsilon less than x, so condition 2 is satisfied. So that's the forward proof. Now we're going to go and do the converse proof. Okay, now let's do the converse proof. So we're going to assume that for all epsilon greater than 0, and for all x in E, x is less than or equal to U plus epsilon, and there exists an x naught in E such that U minus epsilon is less than x naught. And we want to show in the converse proof that those two conditions give us that U is equal to the supremum of E. So the first part of the proof is to show that U is an upper bound for E. So the proof goes something like this. If we're going to show it by contradiction, really. So we're trying to show that U is an upper bound. If U is not an upper bound, then there must be some x in E such that U is less than x. So that's just from the definition of upper bound. And we're assuming that it's not. So if it's not an upper bound, there must be some element of E bigger than U. That means that I can find some positive number, epsilon. If I add that on to U, then I get x. So I've got, if you think about this on a diagram, I've got my U here and my x here. So I'm saying the difference between the two is epsilon. So if I take U plus epsilon, I get to x. And that's going to be true for some epsilon greater than 0. Once I've got that, then I'm going to choose an epsilon dashed that's smaller than epsilon. So that means U plus epsilon dashed is strictly smaller than U plus epsilon, and U plus epsilon is equal to x. So if I write that again, that says U plus epsilon dashed is less than x. But that's a contradiction because we assumed up the top that for all epsilon greater than 0, x is less than or equal to U plus epsilon. So assuming that U is not an upper bound leads directly to a contradiction. So at this point we have U is an upper bound of E, and now we want to show U is the least upper bound. So to finish off the proof, we're going to show that U is the least upper bound. And again, we're going to do this by contradiction. So we know that U is an upper bound. And we're going to suppose that V is also an upper bound of E, but V is strictly less than U. So if that happens, of course, that means that U is not the least upper bound because that's a smaller one. So we're going to try and contradict this assumption. So if we just put this on the real line, we've got U here, we've got V is a number smaller than it, and I'm going to set epsilon equal to be U minus V on 2. So I'm splitting the difference between U and V. I'm saying epsilon is half of that distance, and so when I drop that, that point between U and V, I can write that as U minus epsilon. And that gives me the halfway point. So what have I got then? I've got U minus epsilon must be less than x naught for some x naught in E. That was the definition, or that was part of our assumption. For all epsilon greater than 0, there exists an x naught in E such that U minus epsilon is less than x naught. So I pulled out that x naught and said for this epsilon that we've constructed, U minus epsilon is less than that x naught. But we know that V is also less than U minus epsilon because we've constructed epsilon to work such that this U minus epsilon sits halfway between U and V. And since V is less than U minus epsilon and U minus epsilon is less than x naught, that means that V is less than x naught, and that's a contradiction because we assumed that V is an upper bound. Okay, so V can't be an upper bound, and that means that in fact U is equal to the least upper bound of E. And that ends the proof.